So what is normally done is we do something like like the log, right, which is Laplacian of the Gaussian, and right, which is of course one thing that you do, because it also gives you a control in terms of how much sigma to use. And then Laplacian of Gaussian, you can even apply it at different scales. I mean, I can take one sigma which is very low, and then I can see what is going on. Then I can increase my sigma. I can increase my sigma. So what it means is that as you keep increasing the sigma, right, the structures that are very thin and all will start to go away, because right, you're going to blur them out, and only the very coarse structures will remain, right, as you go higher and higher, in terms of sigma. That is one way of looking at things. That means you have something like a control parameter that you can have. The other thing, right, that you still do is you still don't simply take all the zero crossings, right. What you normally do is you go and do a thresholding on the this one, the magnitude, right. So because you know the zero crossing, right. So what you do is, so you look at the magnitude of the gradient, and then if you kind of do a thresholding, okay, so you kind of see. So what this means is, if there is something that's a very weak edge, right, think of strong edges and kind of weak edges, right. You always have strong and weak edges. We sometimes call them as soft edges, right. So you may ideally want to capture all of them, but then there could be really something that is really weak, right, and then no, it's not even an edge. Okay, so what you can do is you can look at the magnitude of the gradient, and if it is right above a certain quantity, above a certain number, then you can actually use that, do this one, a thresholding, and then kind of leave yourselves with whatever else is remaining, and that should give you a picture about what the most dominant edges are. Edges by which I mean edge, this one, pixel. Whenever I say edge point, if you want to think about it, edge pixel or edge point. Let me just show you some images, right, on that, so that it becomes a little more clear. And many of these things I've already mentioned, okay, during the other lectures and all, but I think we'll just go through the ones that are relevant here. This and all we have already seen, right? Let's not spend time. This and all we have seen. Okay, so this noise and all is here. This and all is very easy. Okay, yeah, right. So here is where what I said is, when you have sigma, right, so you can see that the fine edges and all will start to go away as you start right, taking your sigma up. And this is an edge detector. Okay, this is fine. This is all, I mean, is very straightforward. But let me come to Sobel and all. I've already told you. Okay, now, yeah, right. So here is where, right. I mean, so one of the things, right. One of the things that you can ask is, can I not do a thresholding of simply this one, right? When I said that you can take the gradient magnitude. So let's say, right, something I take something like a Sobel. What is Sobel? -1, -2, -1, 1, 2, 1, right? That's basically a Sobel kernel. So suppose I took that, I can find out this one. I can find out gx, gy. I can find out this one, magnitude, right? Now what will happen if I simply did a thresholding of that? So let's say, right, let's say I simply want to do that. Will that kind of give me the edges? What will be the issue there if I tried that? Looks like that's also a sensible thing to do, because I am anyway saying, right, I want say thresholds, I want magnitudes that are reasonably good, those can be declared as edges. What will be the problem there? One of the three things that I said will get hit. When I said you need an edge, right, there are 2-3 things that I said, right, an edge you need. What is that that might violate? That will violate a single response. See, because what will happen is, see, when you plot the magnitude of the gradient, right, what will happen is, typically, right, you will have, it's not like I mean, so what will happen is, right, you will have something like this, right. I mean, if you kind of, right, think about the magnitude, you have something like this, right. I mean, here is where the peak is. Okay, now when you're trying to apply a global threshold, what will happen is, if you just make this magnitude too high, right, then many weak edges will go away. If you make it too small, then you will be swarmed with a lot of them. Whenever you adjust somewhere, right, what might happen is, all of these, there will be a whole band of guys which will emerge, because you don't know where the local maxima is. You don't know the local maxima. I just know that I have these gradients. I don't know which one of them is a local maxima and all. I just apply a threshold globally. What will happen if I make it too low? Then you will get more and more of these. For an edge, you need one response, but then there will be collectively many guys coming out. Do you see that? Okay, so which is why it's not easy to simply directly take the magnitude of the gradient and use only that information in order to do this one, kind of a thresholding, because that single response thing that you really need, which means that you really ideally need, right, if you have an edge, you ideally need a single pixel contour. You don't want a thick contour coming there, right? You need a single pixel contour. Of course, you can have an edge, right, that goes up and immediately comes down, in which case you will have actually two edges. There is one that is going up and there is one that is coming down, right. So, there you will have two, they can be nearby, that is okay, but that is okay. There you need actually two, because there is one response for this edge, there is another response for the other edge, one is going up, another is coming down, you will have the theta and all accordingly, right, if you are interested in that. But when you have one edge, you don't want a strip coming there, right. So, that is the reason why it is not so easy to simply take the magnitude of the gradient and do it. That is why you have got something like, there is an edge detector that is very famous, that is called the Canny edge detector, right. I mean, it works around this problem very smartly. I will talk about it. Okay, now right. So what okay, now, yeah, unless you know the maxima and all, right, I mean, this is still a problem. Therefore, you can do a Laplacian, right, and then in Laplacian, right, see, for example, yeah, so right, this is simply to show that it is going to be very sensitive noise and all that, therefore you should actually blur it with a Gaussian. Okay, this is Laplacian of the Gaussian. Okay, now you see, right. So what is happening is, if you try to look at the zero crossings, right, when you increase your sigma, right, you see that your zero crossings are kind of giving you more and more, I mean, right, I mean, you are getting significant information, right. So when you traverse from here to here, as you keep increasing your sigma, all the frivolous edges are going away, because see, if you just put everything out there, right, everything is active, everything is important, then it loses meaning, right. So you really want to pick what are significant. But you know what the problem is, even if I showed you the right one, the rightmost one, which seems to have the highest sigma in it, it looks like it has picked all these dominant edges. But even here, if I told you it's a face, would you think that it's a face? Suppose I didn't see anything else, right. Now nobody showed me the person's face, I just showed this image to you. Maybe some of you might say, yeah, I mean, it's an image of a face, but still it's not so clear, right. But then if I did this other one that I said, if I looked at the magnitude of the gradient and I sort of applied a threshold and then kind of looked at it, now you suddenly see a face, right, which looks much more cleaner. Now it looks like I am actually looking at a face. Compare this with the earlier one, right. Again, these are all subjective things, okay. That is why, right, there is no clear way to tell which one likes, right. Somebody might like the other one perhaps, right, but that is the reason why, right, till this point we do not have something like, there is where Canny became very sort of a popular thing, because it had some optimization all inside. Here it is all like, okay, you do this, you will get this, but then there was a good motivation to actually, right, do it that way, okay. That is the way, there is a way a log, if you wanted to right, implement a log based edge detector, this is what you would do. But then a more systematic way, right, in which an edge detection can be done is by going through what is called a Canny edge detector, which I will talk about next. Canny is a person's name, by the way, John Canny. This is a PAMI paper, I think it's 1986 or something. Okay, so this is called the Canny edge detector, and this is actually a kind of a systematic way of looking at the problem, and it tries to address all three things. That means, you should flag an edge only right, if it has a significant kind of a gradient, and it should have good localization, and then it should have a single response, right, all three. So in a sense, right, so it actually solves it as some kind of an optimum, and then it makes certain assumptions that the noise that is there in the image is actually AWG, and very simple assumptions, and then right, we are not kind of, right, we don't have time to go into the details of how he arrives at it, but then eventually shows that the best filter to actually use under that condition, and then the optimization rate is in terms of what you call this one a product of what you call signal to noise ratio versus the localization. Okay, and that product, he says, it becomes maximized when you use a particular kind of filter. What do you think might that filter be that he arrives at as the optimum filter for doing edge detection? Right, you have seen so many filters. Now, which do you suspect might have been the one that he came up with? a derivative of the Gaussian, okay, dog, not the difference of Gaussian, a derivative of Gaussian, okay. So he actually analytically shows this, okay. Now this is more formal, okay, this work is much more formal than the ones, right, that we saw till now. So this is a derivative of the Gaussian, but then right, this by itself, okay, is not really enough. I mean, he has some nice ideas, okay, right, in that work. So a derivative of the Gaussian, and that makes sense, right, because he has assumed noise, and therefore right, that has to be countered. So he needs some kind of a smoothing, and he believes that the best filter to actually use that is this. And then the signal to noise ratio also, right, it's kind of a different interpretation. It's about the say number of the positive edges, right, that you actually capture divided by the right number of false edges that you flag. So signal to noise ratio is not our usual sort of signal to noise ratio. So he kind of constructs the problem around this notion of doing this edge detection. And so the right three concerns are localization, right, strength. So that means, right, it should be it should be a proper edge, and then the third one is single response, right. All this has to happen, okay. Now right, these two seem to be okay, but then the strength, right, by which what he means is that even if you have weak edges and so on, right, but if they are relevant, they should be picked up, okay, right, that's what he means. So what is relevant and what is not relevant, right, we will see now, okay. So the main steps of Canny. Edge detector, and this you will find in your MATLAB and all, right. This is a very open CV, everybody will have this. Smooth the image with a Gaussian filter, then compute the gradient magnitude and a direction. Now, okay, now one of the things, right, that I think I forgot to mention is that in a Laplacian, it's an isotropic operator. It doesn't give you a direction information, right. You saw that, right. You don't have a direction information. You just have the zero crossing information there, and we kind of use that, right. So, but then here, right, compute the gradient magnitude and its direction, right. So now finally, right, we are again coming back to this, that is the theta that I mentioned, right, in the beginning. So that this guy actually uses it. Okay, compute the gradient. So this is like your dog, smooth with a kind of Gaussian, and then take a difference and then compute the magnitude, right, and this one, okay, direction, using a discrete approximation and all that, right? That we know, right, how to do that. Then apply non-maxima suppression. Have you guys heard about this? This NMS in some context. This is not something particular to edges or something. Any other context, has any of you heard about non-maxima suppression? Perhaps, right, you must have, okay. So kind of non-maxima suppression means that when you are kind of looking at several guys coming up, so you want to really throw away the guys which are really not a maxima, so you suppress them. So you can see that single response thing, right, has to kind of, right, do with this, because if there are several things that are trying to kind of, right, trying to tell that we are all important, you want to say that only a guy who is really the maximum should be important, rest of the guys should just go away, right. So that's why this maximum suppression, and this NMS, right, we'll again revisit later in a kind of a different context and so on, to the gradient magnitude. Any gradient, okay. No, any gradient value, okay, yeah, right. This is like a succinct summary of the Canny edge detector. Any gradient value that is not a local peak along the direction of the gradient again, right, this is again important, along the direction of the gradient is set to 0. So then what does it mean? So for example, I mean, so what this means is if I had an edge like this, right, which is kind of going up from a kind of right low to high, and if you were to compute the magnitude, right, a gradient, you will find that, you know, right within this region there are several guys which will have a significant value. If you just directly did a thresholding, many of them, right, may still actually survive. So what it is saying is along the say direction of the increase, right, which is what is the orientation telling you. Along that you try to find out, right, which is supposedly a true maximum, and then, right, the rest of them should go away. So the way, right, so the way it is done is, suppose I take a you know, a grid like this where I am, okay, and suppose right, I'm at this pixel location, right, and I want to know if the kind of gradient magnitude here, should that be suppressed or not. Suppressed means set it to 0, that's it, right, it just goes away. Now, in order to do that, right, so what you have to see is what is the actual this one, right, this one, edge orientation there. Suppose the edge orientation is like this, okay, at that pixel. It could be anywhere, right, whatever, it could also be in some other direction, if you choose. Then kind of what it is saying is that if I were to compare, okay, this with this, if the orientation is that, if the edge orientation is that, then kind of, right, what it is saying is compare the magnitude of the gradient at, let's say, suppose I call this some A, B, C, right. Suppose this is A, this is B, this is C. Then what it is saying is, if the right gradient of the magnitude at A is greater than both C and B, okay, then only right, we will actually leave it there. If it happens to be one of the others is greater than that, then this goes to 0. A goes to 0. Okay, we are only focusing on A. We are comparing the magnitude of the gradient at A with B and C. It survives only if it is actually, right, you know, greater than both C and B. Okay, now, of course, it can also happen that right, I mean, that, for example, it can also happen that the edge orientation is such that you end up somewhere like that, because, right, we don't know which way the edge is oriented. So if the edge is oriented that way, then, right, you might actually end up in a zone where you don't have a direct value. I mean, if you're lucky, you could have a situation like that, right, where you actually end up in a sort of an integer pixel grid. You need not, right, and then what you would do the standard thing, which is again, right, doing some form of right interpolation. You can do a simple linear interpolation, use these two values, whatever is here, and then use how far away is this location, just like I did the earlier case, something similar to that. Assume that, right, it's kind of a delta away from the top pixel, 1 minus delta away from the bottom pixel, do a linear interpolation, get some value here, and similarly get some value here. Again, compare this guy with those two, suppress under those conditions, otherwise it stays on, right. This is what is called non-maxima suppression, and you can see that it's making use of the gradient magnitude as well as the, right, orientation. Okay, both are required, but then it's not over yet. The other key step, right, in Canny is this one. After you have applied, okay, there is something called a thresholding, which you expect will happen, okay, because all the while, right, we were kind of talking about a thresholding and linking, and this is typically called a kind of a hysteresis operation. Hysteresis, right, you all know, okay, hysteresis is something kind of, a memory, right, something that you remember and so on. So here, right, there is some kind of a memory involved, and we will see what that is. And I like this step, right, in the sense that this is one of those steps, right, where you sort of make sure that you don't lose out weak edges. Okay, so the steps are like follows, right. So what it does is mark as edge pixels. Okay, because, right, we have still not said anything. Okay, we only suppressed the things that are not a local, that are not a maxima. Those have gone. It's not like all of them are edge pixels. Okay, now only we are coming to what we would like to declare as an, say, edge pixel. Okay, mark as edge pixels, right. Okay, now, okay, yeah, I think this is the first step. Mark as edge pixels all pixels with Mij, okay, which is, what is M? The magnitude of the gradient at I comma j greater than some this one, a threshold T2. Now this is where this is like a hyperparameter. Okay, this you have to select. Okay, you have to, or maybe, well, you can There is no straightforward way, right, to arrive at it, because depending upon how you choose T2, you might actually end up with either, right, a little more edges than what you want or a little fewer than what you want. Okay, this is a hyperparameter T2. Then mark as non-edge pixels. That means these are really not edge pixels. Non-edge pixels. All pixels with Mij less than T1, some other. So right, this is like a high threshold, this is like a lower threshold, which means is that something that is weaker than that, don't even accept it, throw it away. And some people say T1 can be taken as T2 by 2, but again these are all heuristics. Okay, some amount of heuristics of course is involved. Then what about they say rest, right? You have these guys that are lying between say, right, T1 and this one T2. Okay, we are still undecided about them. What would you do? Those are the weak, those are the soft edges, right? Because you have something like a very clear edge which you can clearly see, exceeds a certain threshold, clearly declare as edges. Something which is very weak, very clear, goes away, right? What do you do with these, right, middle guys? You want to be able to use them, you don't want to throw them away. So huh? No, actually it's smarter than that. I'll write it down. Okay, so mark as edge pixels, all pixels. Okay, mark again. Okay, mark as edge pixels, all pixels with M of Ij greater than T1 but less than T2 that are 8 connected. That are 8 connected to at least one pixel with Mij greater than T2 along a chain of pixels. This looks a little verbose, but I think chain of pixels with, what do you think? With Mij greater than T1. What does this mean? See, when you say 8 connected, right? So what it means is when you take a 3 cross 3 window, when you are sitting here, there are 8 of these guys right around you. That's a 8 connected neighborhood, right? If you take a simple 3 cross 3 window. So what it is saying is, right, between so all those pixels that have a value between T1 and which have a magnitude of the gradient, that's between T1 and T2, right? So what it is assuming is that in a real world, right, there is going to be linking up, right? There will be like, there is going to be a continuity, right, and so on. So what it is trying to say is, if a path exists from that pixel, right, which has let's say a gradient between T1 and T2, but if a path exists which should be right within this 8 pixel neighborhood, and right, and through this 8 pixel neighborhood, if you can arrive at some other strong pixel, but then when you go through this, right, I mean you should be able to go through pixels that have Mij greater than T1. It should not be through the other guys, right, which you have already knocked off. So it means that if there is a weak link, right, because the T1 and are all like just about T1 are all kind of, right, weak guys, right. So what we are saying is, if a weak guy has a link to a strong guy through a chain which can be a simple local neighborhood. Why local? Because edges and all will have some spatial relationship, right. So what it is saying is, if that path exists, flag it, because very likely that you threw it away because there was a gradient that was weak or something, and then you seem to think that it's probably not an edge pixel, but in reality it might be there, because that's how natural images are formed, right. There is always a continuity and so on. So this idea of thresholding and linking. So linking is the step where you link a pixel, you really declare it if this happens, otherwise you say right, it's not an edge pixel. I mean, right. So actually clean idea, right. I mean, makes sense. Okay, and if you do like this, right, and you should okay, I'll just show you a few examples, right, just to show how canny works. I hope I have them. Yeah, this and all is there. So, derivative dog of, so here you have dog, non-maxima suppression, this and all I told you already. So, right. So, here is how it is. So, if you do a non-maxima suppression, see this kind of a thickness that you see there, right. That is what I meant by not a single response, right. And see this, right, after you do this non-maxima suppression, right, you kind of see removed all those thick guys, and then hey, something should happen, no? Is that the last one? No, okay. Then you go through the strong edge, weak edge. Okay, this one for some reason. Then you do this, okay, and effect of the Gaussian. So again, the same thing, right, that we had there. We can again have. Oh, I think this is not in full screen. Okay, so again, right, what we had there, right, we can also have here. So, for example, right, you can have a sigma that is small, sigma that is high. Again, you can run canny at various sigmas, because there is a derivative of Gaussian sitting there, right. And you can see that the edges that come out are actually quite nice, and you can have situations where you want to combine the edges and so on, right. We are not going to get into that, but as you can see, right, it's a more systematic way of kind of using all that we learned in terms of gradients, orientation and all that, all of them brought together in a sort of a nice framework in order to solve a fundamental problem, which is one of finding edges. Okay, so I'll stop here.